Okay, I'm ready to start. I'm Daniel Lizot from Team Sweden, and I'm presenting problem number 15, blowing bubbles. The problem formulation states, when blowing on a soap film in a ring, a bubble may be formed. The liquid film may pop or continue to exist. Investigate how the number of bubbles produced from a single soap film and the characteristics of the bubbles depend on the relevant parameters. So it tells us what to achieve, bubbles and the liquid film, and it tells us to investigate the number of bubbles and the characteristics of bubbles in terms of the parameters. So an outline of my presentation. I'll go first through the basic physics of how the bubbles work and some observations that we make. Then a bit more advanced theoretical model, again, for the fluid dynamics of the system. Then I'll talk about my experimental investigation where I vary the parameters and look at how the bubbles change. Then I'll summarize my results and I'll look at the conclusions from my research. So, looking at the relevant parameters that we think are important for the system, when talking about the soap solution, it's very important to consider what ingredients there are in the solution that can change viscosity and density. But the most important is how the surface tension changes, and that we will explain a bit further. So the next thing to investigate would be how the properties of the soap film, which has some elastic properties that are inherent due to the surface tension, and we can investigate mass and diameter of this film. Then we need to look at the airflow and how the velocity of the airflow and width account for different fluid characteristics. And then when we investigate the soap bubbles, we can look at the size and the quantity formed during the experiment. So looking at the soap solution, the inherent property of soap molecules is that they're amphipathic, which means that they have a hydrophilic end, which is attracted to water, and a hydrophobic end, which is repelled by water. This means that if we have a large amount of soap molecules that are in contact with the water surface, they will create a film. And another thing, since the hydrophilic heads attract the water molecules, the soap film can lower the surface tension of the water surface. So what happens when we create our film in our experiments is that the soap molecules are arranged in 2 rows above and under a layer of water. And as we said, this can decrease the surface tension until a critical point, when the soap concentration passes the critical micelle concentration, which means that after that point, micelles will be formed, which are these spheres of soap molecules, which don't contribute to the reduction of surface tension. The soap layers that are above and underneath also help the conservation of the film by preventing evaporation and ensuring that the bubbles don't collapse on their own weight, creating a very thin film. So now looking a bit more into the advanced physics of this. So 2 numbers that we need to consider in this experiment, 2 important concepts are the Weber number and the Reynolds number. Now the Weber number describes the characteristics between the inertia of air, so the kinetic energy of air, and the surface tension energy of a film. And basically from this Weber number we can say that when the Weber number is high, it means that there's enough kinetic energy to deform the film, and that's when bubbles will be formed. The Reynolds number is used to model turbulent or laminar flows in air, and it is based on the density and the viscosity and mainly the velocity of the air. And in our case, we determined the Reynolds number for most of our experiments to be around the range of 10,000. So this means that our flow will be turbulent, for sure. Now, we can use this assumption of turbulent flow to take into account a console simulation that will model how the airflow disperses from a nozzle. And we find that after repeated simulations that there's a constant angle of 23 degrees at which the flow expands. Another important concept to note for this research is the Rayleigh plateau instability concept. That basically describes how perturbations and turbulent flows can cause the formation of droplets in liquid streams. Now, our bubble is not a liquid stream, strictly speaking, but in the same manner as a liquid stream would form a droplet, in our bubble, the fact that different oscillations can cause the membrane to become thinner at a certain point causes the surface tension to increase and create the bubble detachment phenomenon. So what's going to be important to note for later is that we use an extreme value distribution to model our results, especially on the bubble counts. This is because we have a very large spread in data and a very unstable phenomenon, as small variations in temperature and pressure can lead to a premature breaking of the bubble. So it is important to have an appropriate statistical model that can give us the most likely value of bubbles, where we can manipulate the scale and the spread of the data, and where we can manipulate the shape of the distribution, and this is especially in the extreme value distribution. We can change whether the probability will be higher at the start or at the end. We can turn this around by modifying that C value that we saw before. So what happens is that when we take our data, we take the cumulative frequency of our bubble counts, for example, and then from this interpolated line, we can estimate a probability distribution for our experiment. But more on those results later. So talking about our experimental investigation, the airspeed and different parameters was investigated with a pitot tube that looks at difference in water height. And one of our first experiments was to measure the surface tension of the soap solution. So what we did is we changed the soap concentration, and we measured the surface tension with a tensiometer, which looks at when there is a critical mass that is enough to let a droplet fall. That is when we encounter the critical maximum surface tension of the liquid. What our results show is that we can increase the soap concentration until a point where there is no further decrease of surface tension. And this supports our idea of the critical micelle concentration, which then prevents the surface tension from being decreased further. Now, looking at, we investigated how the lifetime of a simple soap film on its own, without being disturbed, would change. And our conclusion from this was that even though we change the diameter of the ring, there will be no significant change in the lifetime of the bubbles, which means that it's not about the quantity of soap that we put into the film. It doesn't define the lifetime or the surface area. So then in our later experiments, we use this setup where we have a tube connected to an air blower, which blows air onto a film, and we can vary the nozzle distance and the airspeed. So, and then we can measure with video analysis software the sizes and numbers of the bubbles, and also parameters from this cylinder, which will be talked about later. So, first of all, let's look at how the bubble diameter changes with nozzle distance. And here we see a linear increase, or not linear increase, a general increasing trend, which is justified by our console model. Since the flow of air expands, it creates larger bubbles, which, So then we investigated how the bubble diameter changes with airspeed. We see there's a decrease of bubble diameter with faster airspeeds, and that is because the faster airspeeds will cause the bubbles to have less time to become large and detach faster. Then we talk about how the radius of the bubbles changes depending on the time that it takes to form them. And we can actually use a concept from the Rayleigh plateau instability to calculate the proportionality between the radius of the bubbles. This is supposed to be a tau. So, and the time it takes for them to form. And we see that when we plot this in a log scale, we have a 1.5 gradient that is very consistent with our data. Now, we investigate also this soap cylinder and how it changes with different air velocities. The length of the cylinder increases for higher velocities, and the diameter of the cylinder decreases when we increase the velocity. This can be explained by the fact that a higher velocity will give a higher energy to the film and cause it to stretch more, and by surface tension also become smaller. So, a quick illustration of the sheer scale and range of our data. These are just individual data points plotted that show the bubble counts. And we see they have a huge range, so we thought of a way to summarize this data, and as we said before, the extreme value distribution is the method we use. So I talked about how we take the cumulative frequency graph, and then from that we can plot our probability distributions. So here I can compare data 1, data 2, and data 3 probabilities, which have about 300 trials each, to see what happens when we change the velocity of the air and what changes when we change the distance from the nozzle. What happens if we increase the velocity is that we have a less spread in values. This is because a turbulent flow will create a more unstable film that is more likely to break. And we also have a higher peak number of bubbles. And this is caused by the fact that a higher velocity will cause bubbles to be smaller and detach more quickly. On the other hand, if we look at, we increase the distance from the film, we see that we have, again, less spread in values because a slow flow creates these big bubbles which are very unstable. But we still see a higher peak number, and that is because once a steady flow is achieved, once the air overcomes the surface tension, the motion is much more stable. So, yeah. So this is just a small representation of the different data sets that we recorded. And we see here that the higher speed creates these smaller bubbles and a higher detachment frequency, and the increased distance creates this much more unstable large bubbles. So moving on to our conclusion, I'd like to point out that we achieved bubbles and the liquid film, and we investigated the number of bubbles in relation to relevant parameters. The characteristics of the bubbles, the film, and the soap cylinder were all investigated, and the problem formulation clearly states that bubbles may be formed, which in our opinion justifies us taking a probabilistic approach in modeling the distribution of our bubbles. Thank you.
Thank you. It's time for questions from your audience.
So first of all, I'd like to know the FPS of your camera that you use for the video analysis. The short.
500 FPS.
500 FPS. And how did you calculate the specific surface tension in which the bubbles first started to form? Do you have calculations for that, first of all?
No, I don't have the
Okay,
calculations.
we'll talk about that later. And so, do you think there'll be a difference if you place the film vertically? Because in some cases you place it vertically.
Because the soap can drop to one side and then drop off it.
And how did you ensure that there was the same thickness of the film every single time you conducted the experiment?
We didn't, and that's one of the things that lead to this large spread data.
Okay, and so because of gravity there forms a small droplet in the center of film. Do you think that creates some differences?
We
Yes or
only
no?
perform, it would, but we make sure that that doesn't happen.
Okay, what were some of the assumptions of your theory?
Which theory exactly are you talking about?
So for the number of, the probability of the number of bubbles formation.
Well, that is just a display of our values. We don't have a theory of
Okay,
prediction.
and what factor do you think defines the lifetime of the film itself?
There's mainly the drying of the film and the interaction with other particles of the air.
Okay, and how did you control your flow of your air? How did you control the flow rate of your air?
For it to be constant,
Yeah.
I think you're addressing
Just
something.
the measurement, just the apparatus.
Well, we have a special valve for that to make sure that
Okay.
we ignore the build-up phase of the
Was this
machine.
connected to a machinery or?
Yes.
Okay. Okay. And do you think braided, braided or simple film matters? Does it matter if the film is braided,
Braided.
around, yeah, or if it is simple with a wire?
Okay, so that's an optional answer now.
I think that has an effect on the lifetime of the film.
Okay, thank you. And please proceed with preparation of your position. Okay, please talk to the opposition.
Okay. So,
Would you please start talking? Thank you.
hello everyone, my name is IYPT and today I'll be presenting my report on the opposition for problem number 15, blowing bubbles. So first of all, let's move back to the problem statement. It requires us to form bubbles from liquid film. So the crucial part is that the liquid film may pop or continue to exist, and we are required to investigate how the number of bubbles produced from a single film vary and how the characteristics of the bubbles vary in the report. So the fulfillment of the problem statement by the reporter, where we find that the explanation of the basic qualitative explanation of the phenomenon was done very well, and he described the reasons for why bubbles form in the first place. However, we find that there was no condition for why the bubble may, for why the film may pop or continue to exist, and or why the in what cases the film will make a single bubble, and in what cases it can make multiples. And we find that the number of bubbles produced from a single film, however, they did investigate that, however it wasn't reliable, so we think it wasn't done efficiently. And for the characteristics of the bubbles, we also think that they investigate it to some certain extent. So for the good points of the theory, we find that there was sufficient explanation of the formation and component of the film. They talked about Weber numbers and the Reynolds numbers, and they had a simulation in console for the turbulence of the airflow, and how that would depend on the distances, and they calculated effects of velocity and concentration, which we find was very good, nicely done. However, there were some bad points of the theory. As mentioned earlier, they never defined the conditions for when the single film will form and when multiple bubbles will form. They never defined the range of velocities from when bubble starts to form in the first place to the critical velocity, and the velocity when there will not be any more bubbles formation. And then they had a lack of proper model for the deformation of the film and why how bubbles form in the first place for the initial instant, and they never talked about pressure, which we think is important and really crucial to the problem. So for the experiments, we think that there was a reliable experimental setup for the surface tension. They used a tensiometer for every case. They investigated most relevant parameters, however they weren't investigated to a reliable degree. And they talked about probability, which we think was fine in cases of number of bubbles, because that has some certain chaos to it, or uncertainties to it. So the bad points were there was many uncertainties of the thickness of the bubble. In each case, they never checked if they never ensured that the thickness was the same. They never accounted for the film thinning over time of the bubbles and how that would affect how that would eventually make the bubble pop, and they had unreliable comparisons, so there was a lot of deviation, and they thought that is one of their, they agreed that that is one of their weaknesses. And there was no clear depiction of the setup, so they never told us that they had valves to control the airflow, and when questioned, only after questioning did they show that part. And so that is all. We'd now like to invite the reporter to discussion.
Yes, if you don't mind, I'd like to address one of your first points, which I think is very interesting. The conditions for the popping of the film. So I think you have a good point that we didn't set clear conditions for why the film pops. I'd like to maybe list a few factors that could be involved. So I think that we have drying.
So that is the thing of the bubble.
of the film,
Film.
right? We have the particles in the air that are dry. That
How does
Can-
that affect?
so if a bubble comes in contact with a dry surface,
Yeah.
it
It
pops
may pop,
immediately,
or yeah.
and you can have small particles in the
But
air
that could be controlled
interfere.
by having so not
If you-
dusty setup and having
Yeah.
plates for the bubble to grow, and I think that is one way to control it.
I think it's very, very difficult to control, but I see, ideally, yes. And I think there are, oscillations
Oscillations
of the film,
of the
both
film.
in the bubble case and but especially in the case when the bubbles are, when these oscillations reach like intensity, that can lead to breaking of the
So
film.
so do you have any certain formulation or
No.
any way to formulate that?
No, but I have a good reason for it, is that
Yeah.
these parameters are extremely difficult to, are oscillates at temperature.
Yeah.
These are so small changes that they're extremely difficult to detect. So this is why we approach this problem from a stochastic point of view. We know it's a very unstable phenomenon, and that's why we use a probabilistic approach to measure the average
We
relationship.
see that in your probabilistic approach there was a lot of deviation. There wasn't a certain limit. You never defined a certain limit after which you think won't be any deviation. You know? Does that make sense?
I'm not sure what exactly you're referring to.
We'll move to that later. Let's just first focus on the conditions for the popping. And so for the drying, we think you could have added glycerine, so that has a lower evaporation rate, and so that is how you could have controlled this factor. Do you agree?
For the drying,
Yeah.
I don't know the properties of Listerine that would prevent drying.
So the glycerine has a
Glycerine.
lower rate of evaporation than water.
Okay.
Do you agree?
Yeah, I think that's a
that is
valid point.
one way to do that. And so the particles, we find that it would have been easy to just control the amount of dust, and so control obstructions within the way.
I'm not talking about macroscopic particles, I'm talking about very,
All right.
very tiny ones.
Let's move on. So why do you think what happens why a single film produces a bubble and still continues to exist?
Yes.
What happens?
This is because of, so there's a Rayleigh plateau instability
Yes.
involved in this.
Agreed.
What happens is that when the jet forms this thinning of the layer, here the surface tension is increased, and that will cause it to shrink and merge.
We agree with the reporter, and we think that the description is valid because the surface tension then has a higher role than the instability of the film, and so it finds it easier to make a bubble than to exist in such form, and so bubbles form and the film.
I would also like to add that the pinch off moment is where the bubble is, or the film is most likely to break. That is the most crucial moment, because if there is a small imperfection in this point at the pinch off, then the whole membrane breaks.
And so now can we come on to critical, do you think that there is a critical velocity before which the bubble cannot be formed?
Yes.
Yeah, and so did you calculate that? It was pretty
I don't have it in here. I know that from doing the experiments, there's a range of between
Do you
before
have
3.
experimental data that supports
I don't have it here. I'm sorry, but I know that at very low velocities, around under 3 meters per second, and above, let's say 7, 8, no bubbles will be formed. Yeah,
Oh.
meters per second.
Okay, we think 7, 8 isn't very reliable, but we will agree with that.
And then again, velocity alone
So-
can't be taken independently, because we also need to consider the distance of the nozzle.
So, okay, and in some of your, can you move to the pictures of your film, of where your films are forming?
You're talking probably about slide 28.
Yeah.
This?
So,
Yeah.
we have some cases where your film is some cases where your film is placed downwards. So that creates a film somewhat like this in the initial case, because there is some accumulation of water.
So that is entirely dependent on how much soap we add. And effectively, when we do dip the ring into the soap, we make sure that we drip off a little bit of it so that this droplet isn't formed. But I agree with you that if that droplet was there, this would have a significant effect on the film because a force pulling the film down will already create an elasticity condition.
Yes. And so you talked about elasticity, the factors of elasticity, but we don't see any relation with that in the
No. The main thing I was referencing with that was the surface tension of the water, which causes the film to minimize the surface area.
And so, when counting the number of bubbles produced, did you take into account the radius of the bubbles or the number of bubbles?
For a single, when we did a single setup with a single parameters.
That up, please.
You mean, let's see.
That fell also, we don't know these side numbers.
You are talking about this, for
no.
instance?
So, where you have lots of deviation, where you had random data points.
Do you know, was it at the start?
I don't remember, you know, the slide number fell out. How many slides you have?
Is it, no, it's not this one?
So, alright, we'll move, we'll just skip that.
Sure.
Yeah. So, other requirements of the problem statement were to find the characteristics, and we feel that you investigated the radius of the bubbles. And did you investigate the longevity of the bubbles formed?
No, I did not investigate that.
What do you think that depends on?
I don't think, I think that can depend on how much, well, we actually investigated that it doesn't matter how much soap a film has for it to survive. So we say that actually there will be no dependency between the lifetime of the bubbles.
We just agree with the reporter on that because we think that the thickness of the bubbles defines how much longevity it will have. So after some time, if the film is thick enough, it will take longer time to thin and collapse under its own pressure. However, when the film is thin to begin with, it will affect the longevity of the bubbles, and that we think that is one of the characteristics of the bubbles that they had to investigate, but they never did so.
What I want to comment on that is that I would actually say that the film thickness does not, or the bubble thickness does not vary in a considerable matter unless we change the soap concentration.
So how does the bubble collapse?
The bubble collapses due to the same things that we talk about here. Drying, particles,
Sorry,
oscillation.
but we disagree. We think that the bubble mainly pops because of the thinning of the film. And we think that this is the most reasonable.
Do you mind if I ask a question about that? So this, let's say here you have your water.
We can disagree because we don't have a lot of time.
Sure, fine.
So, what was the, sorry, lost. So, yeah. And so, points for discussion, requirements of the problem statement. So you controlled velocities using a wall, but how was the velocity presented in the first place? Did you use a compressor or?
Oh, we used an airflow.
Yes. How did you ensure that it was
a constant airflow?
Yeah.
Well, we did repeated measurements on the airflow to see how we found that the airflow was constant.
And what was the average deviation?
So you can see that we have larger deviations in the small velocities. Here you can read it off pretty much 0.2, and here maybe a bit larger. 0.4.
So was your ideal case in this scenario or
this is where we have the least error in the air velocity.
And is that where you conducted most of your experiments?
Yes.
Okay.
Even though you can see in other plots, when we have large uncertainties in smaller velocities, this is explained.
Okay, and can we move to the probabilities?
Yeah, the ones I showed before?
Yeah.
Yes.
And so, estimated probability distribution. So we find that there is a certain amounts of bubbles that can be formed. So why do you think that it does not exceed this limit?
So this is one of the features of the extreme value distribution, that it reads off the probability, and we know that...
Was this theoretically calculated? Or
no, this is the data that we collected, and we compiled.
Do you have a theory for that?
No, we don't have a
Do you think
prediction.
the theory agrees that there is a certain limit to the number of bubbles formed?
Yes, let's say it's not like a discrete limit, but the probability after 250 is so low that it's not possible.
We agree with the reporter, and we think that we agree that there is a certain limitation to the probability. And okay.
We know intuitively that the film cannot blow into the bubble.
One last question. One last question. So, what was the time taken for a single? What was the time taken for a single film to produce the bubbles?
We have an average of about, let's say 10 seconds, but it varies
After that
depending, depending on how many bubbles are blown though.
Okay.
It varies.
Alright.
Okay, may I ask the opponent to summarize the discussion?
So, okay, so we had a very fruitful discussion where we pointed out some of the weaknesses of the reporter's theory, and they agreed that the system was very chaotic and they could not do so. And we think it was kind of a reasonable thing to do because the formation of bubble is dependent on many parameters which could not be controlled experimentally. And we first discussed the initial conditions for the bubble to pop and for the film to exist or pop, and we reached a mutual conclusion that depends on the air velocities, and that depends on such uncontrollable parameters, and that these could, however, some of them could be controlled by the reporter. And then we talked about how the probability would drop down to 0 or be very finite, and we reached a mutual conclusion on that. And we also talked about how the characteristics of the bubbles would vary regarding changes in velocity, and we again found mutual conclusions. Thank you.
Okay, thank you. 3 minutes time for the review of the first question.
Okay, the first question is for a reporter. Do you control environmental factors?
As much as possible, yes.
What environmental factors did you control?
Well, I mean, we did the experiment in the same room. We had room temperature, room pressure.
How about air pressure?
That's what I said, like the normal air pressure.
Okay, next. Then, what is the probability distribution? What's the physics meaning behind it?
Sorry, can you repeat the question?
What is the number of bubbles probability distribution?
Yeah, because we have a very large spread in our data, so we can't find
So
a
what
single.
caused that large spread?
Because it's a very stochastic and unstable phenomenon.
You mean the soap film?
The soap film and the system itself is very unstable.
What about the coding?
So we agree that this system is very uncertain, and so we have a range of the number of bubbles
Okay,
formation.
thanks. And you mentioned that you use extreme distribution to describe the phenomena. So what's the basic meaning behind it?
So the properties of the extreme value distribution is that differently from a normal distribution, only one end of the curve starts with a high distribution.
Excuse me,
and
what's
it
the
ends
basic
here.
meaning of this distribution?
What do you mean by the meaning? We can find the most likely value, and we can find a maximum value. That
Okay, so it's about mathematics.
Yeah, it's a statistical method.
Okay,
Yes.
next. Then, what characteristics do you investigate on? Except for the number of bubbles and the diameter of it.
Well, we show that we have number of bubbles, diameter, time for it to be formed, about the soap cylinder, the size of
Did you
it.
try to investigate on the thickness of the bubbles and also the lasting time of the bubbles?
No, but I thought that was irrelevant.
Okay, and what surfactant do you use in your experiment?
We use sodium something, SDS it's called?
SDS?
Yeah.
Okay, then what do you think will happen if you try the different surfactants?
Mainly the effect on the surface tension can change.
Okay, so the opponent have mentioned about the popping condition.
Yeah.
So what do you think, under what exact condition will it pop?
So we think that one condition is because of the high pressure exerted, because of the pressure differences within and outside the bottle, outside the bubble, that would be one reason for the film to pop, and other reasons would be thinning of the bubble.
And about the protein, you mentioned that the expansion will lower the surface tension. So what is lower surface tension good for bubble formation?
Because water on its own has a too high surface tension,
Yes.
and it would collapse the bubble on itself due to this force.
Okay. Also, you mentioned that you can add sugar. So what's the physics behind adding sugar?
Well, we can change the viscosity of the liquid.
Okay. Thanks.
But
Okay, thank you. Hi, sorry.
the reviewer from Taiwan, now reviewing part number 15, blowing bubbles. So first, the reviewer believes the main focus here is first the formation of the bubbles and some conditions necessary for during phenomenon, and also the relevant parameters that will affect those characteristics. So first about reporter's outline, in the observation he justified some assumption which is quite clear, and for his theory he used a string value distribution to try to explain the result, but there's no clear connection to the experiments. And for the setup part, they will control the flow rate, which is quite good, and for experiment that have a lot of experimental data and mega distribution, but there's entirely missing the characteristics such as the lasting time and the thickness. For the conclusion that don't show the qualitative comparison with the theory. And for the opponents, we find some pros which is that point out many flaws in experimental control and that clarify many processes of the bubble formation and some reason. For the cons, it did not try to clarify the qualitatively comparison between the theory and the results. And for the discussion part, the first the opponent asks about the lifetime of the big film, and the reporter said there are some factors like evaporation, the particles, also the oscillation of the bubble, and the temperature will affect these characteristics. And the reviewer believes it is the responsibility of the reporter to try to control as many as environment factors as possible to make sure those small factors doesn't affect the phenomenon. And for that last part, the opponent asks about the radical instability, where the reporter agrees with the opponent that the pinch is caused by the small disturbance. And the reviewer believes also we can try to use the energy analysis between the Laplace pressure and the kinetic energy provided by the pump to find out the threshold that bubble can begin to form. And for the position of the ring, the reverse thing that use the horizontal because the gravity will not affect that much, and the reverse agrees with that. But also the gravity will cause pulling in either setup, but horizontal setup is more symmetrical and thus make it more accurate. And I also talk about why the bubble may pop, and the reverse thinks that it is independent of the amount of salt water not caused by thinning. And the reverse thinks if the experiment is controlled very well, we can see some relationship with the evaporation rate. And also, the reporter did not measure the thickness of bubbles after they forming they can try to use the interferometry to analyze the thickness of the bubbles. And I also discussed about the effect of the Chevrolet, how to control some environment and also time scale as experiments. Some points missed are, the first is the physics meaning behind the probability distribution. That I've mentioned about the non-instability and also some, but a reporter believes that when the cell film is extending, there might be some concentration flow in the cell film and thus cause more random factors. And next one, they didn't talk about some characteristics of the bubbles like thickness and lifetime, which is quite important because thickness might affect, also is a very obvious characteristics, and the lifetime might also depend on many other parameters. And they also didn't explain much about the effect of environmental parameters such as the temperature, what will happen when we conduct experiment at a very high temperature, and also air pressure and the humidity. Thank you.
Thank you. And there's 2 minutes time for concluding remarks by the board.
I'd like to thank the opponent and the reviewer for very interesting points. I'd like to reiterate that I think the idea of replacing glycerin with water is a good way to change the evaporation rate. I want to talk about both what the opponent and the reviewer mentioned, which is a lot about the conditions and parameters and environmental factors that could be controlled better. I agree, they could be controlled better, but that is for every setup, and that is something that does not take away from our investigation. I think it's a very general kind of question. Then when we talked about the conditions for the bubble to form, I agree that this is very important to understand the phenomenon, but I also think that it's very difficult to quantitatively measure these parameters and the conditions for the bubbles to form. To conclude, I want to end by reiterating that this is a stochastic phenomenon, and we have used the appropriate statistical methods to describe it and performed literally over 1,000 experiment trials. From these, we have made numerous conclusions about how relevant parameters affect the number of bubbles and their characteristics. This is why we consider the task is fulfilled. And just to bring it back to the problem formulation, a bubble and film may be formed. They don't give clear indication that we need to have a quantitative determination of this. And this is, as I say, very, very difficult because the phenomenon and the atmospheric conditions are very unstable. Thank you.
Okay. So 5 minutes time for your questions. If you don't mind, I would like to take the first question and direct it to the opponent as well as the reviewer. First, for the opponent, you claim that the thickness of the bubbles should have been measured. Can you propose a method can you propose a thickness measurement that would be appropriate for that experiment? And the reviewer, can you propose one as well?
So we can do that by spectrometry, by passing light through it and found the refraction and then calculating simple geometric relations of the refractions.
The reviewer?
We agree with the opponent that we can use the interference of the light to measure the thickness.
Okay, thank you. Eric?
So both the opponent and the reporter during your discussion, you made this drawing there when the bubble detached. And you said it's due to the reason that the surface tension at that point increases rapidly. Could you give me an argument why the material parameter of the film should increase at that position?
Material parameters means?
The surface tension.
So okay, so because we find that in this case because everything returns back to minimal potential energy, we find that in this case it is better for the film to exist as a simple spherical shape than be deformed as it is. So that is why it detaches.
I agree that why the surface tension works this way, it's because it wants to minimize surface area, but I don't think that the material property of the film is altered.
So
It's
because you
just
both said in the discussion that the surface tension increases there.
yeah, that was a mistake on my hand. I would like to reiterate that at this point it is easier for the bubble
Can I
to
just
detach.
clarify that I never said the surface tension would increase, but I said the effects of the surface tension would increase, so it would find it better to form a bubble than be deformed.
Question for the reporter.
Yes.
What is the temperature of the room?
That's room temperature. What do we have in Sweden?
So,
20 degrees.
But how can you calculate the Reynolds number? How did you come up with the Reynolds number?
Well, based on the density of air in Sweden. And
But don't you need to know what is the kinematic viscosity that you use to calculate the Reynolds number? Because you need to know the viscosity. In order to know that, you need to know the temperature. So
yeah, but we take that into account when we calculate the viscosity.
yeah. So what is the temperature that you use then?
Yeah, so it's about 20 degrees.
20 degrees. Okay. So now it's going to be the question for three of you. So this is like the ring, right?
Yes.
So this is the nozzle normally. So what happens if you change the direction of the nozzle by that? So what happens to the characteristic of the soap?
Can you specify who is to answer first?
Oh, sorry. The reviewer.
Okay, first I believe that will affect the cross-sectional area of it, so it will affect the cross-sectional area of the airflow, and therefore it will it will affect the cross-sectional area of the airflow blowing on the soap film, and thus change the diameter of the bubbles.
So
Okay, how
we
about
think it would affect the dimple form, and then it will be more bubbles but smaller diameters.
The reporter.
I agree that this causes a breaking of the symmetry in our model. So this means that the bubbles will detach in a different way. Most likely it's more unstable than the straight one because the forces from the surface tension are unequally distributed. So we will have less bubbles, in my opinion.
To the reviewer, you mentioned that the reporter should have a more precise control of the environmental parameters.
Yes.
Could you specify, to your own opinion, which of the parameters could be like precisely controlled?
Temperature should be controlled precisely because temperature will affect the surface tension of the solution.
So it's mostly temperature.
Yes, that's very important. Also, the humidity should be controlled because it will affect how fast it evaporate.
How do you control that?
We can do the experiment in the same day. Also, we can put some water to increase the humidity in the room.
Okay. Eric?
The question to the reporter, you brought up the Weber number. Did you somehow maybe use the Weber number to find a condition when the bubbles form?
Not really. It's well, we use it when in our assumption for the plateau Rayleigh model equation that talks about the time for the bubble formation.
So what? So you use what condition on the Weber number? Did you?
So we use the air velocity and
So
the
you just
surface
calculate the Weber number? Or
Yeah.
what?
we measured it from our experiments.
And what can you say about that?
That when the
Weber
bubbles
number
are formed, the Weber number is larger than 12, and when they're not formed, the Weber number is lower.
Okay, thank you. And we move on to grading. Okay, seems like we're all done. So please show your mark out from my side, it's 7, 7, 6, 5, and 5. For the opponent, please. It's 7, 8, 7, 5, and 6. And for the reviewer, please. It's 6, 6, 6, 4, and 6. So Eric, seems like you got to comment a lot. Let's, okay, maybe you can have your justification on the low mark and on the report, and then Eric's on the low mark.
I do believe that the reporter didn't have studied all the characteristics of the soul, but it's kind of reasonable because like it's kind of complicated. But one of the parameters that you need to somehow include in the presentation when you talk about the fluid dynamics, because we talk about the surface tension and stuff like that, is the temperature. Otherwise, like how can you approximate the rate of number and stuff like that? That's like really crucial.
Okay, being on the other end of the scale, like having assigned 7, I guess. Yeah, 7. I think your standard clearly was the above average report I would expect on that problem. As I feel like this is one of the more complicated problems that you can deal with of the recent problem set. And I really like the idea of like reducing the problem to the point that we can actually make any suggestions from, and not like insisting on a theoretical model that would only hold in a very, very narrow window of investigation. And I really envy your honesty of like stating, okay, this is a problem that has a widespread in statistics, so we're treating it statistically. And I felt like this was an appropriate method to actually tackle that problem. And I really like how you actually tried to gain some knowledge from there. However, there's like some drawbacks to the solution. Like for example, as the opponent and the reviewer pointed out simultaneously, like the thickness of the air bubbles could have actually been investigated. And I also agreed to the opponent as well as the reviewer that the formation of the bubbles, like the opponent tried to clear out, could have been investigated in greater detail. Okay. For the opponent, we have a no mark of 5 by Eric.
Yeah. So well, maybe to explain the grade for the opponent, I quickly have to say something for the reporter. I thought you did excellent job on the experimental part. Full credit for that. But on the theoretical part, I mean, I do not expect you to have a complete model. That's not possible. But you could investigate when does the film form as a function like critical velocity or something like in this range as a function of time. At least up to a proportionality. I think that is possible. And if you do think, if you have some simple models like that, you will get even higher. You will get higher. For the opponent, I thought you were discussing more superficial parts of parts that I think are not that relevant. That is like the popping of the bubbles due to disturbances and stuff. I think that that is also a factor, but I think he accounts for that in the large statistical spread, and I think that's valid. I mean, just discuss exactly why these bubbles pop. It's quite hard to exactly give these examples. So I think also the discussion, I think it was about, I was hesitant to give you a higher grade also because you didn't go into these things like discuss more these things that you had there with the when does the bubble detach, could you give a condition, how does that translate, how could you use that then with your data, more in that direction, I would have.
Okay, comment on the 8 by diagram?
Yes, it was the best opposition I said in this year, and you have asked many questions I asked, and your approach in discussion, I like it.
Okay. Comments on the reviews have been quite uniform, mostly 6s except for the 4 by Eric. Eric, do you want to comment once again, please?
So, I liked the presentation you had gave, we said we considered the dynamic pressures equal to the Laplacian pressure and Dacing could use for an onset condition, which I really like. On the other hand, I thought the questions were not that good, or at least very, not that, it was not the main issue of this presentation. It's not, his biggest problem is not that he cannot perfectly control his initial conditions. For me, it's more, it lies somewhere else. So we did make the points in the questions. And the thing with the interference patterns on the moving bubble, I think that is spherical. I find that's probably quite hard to calculate the thickness. Yeah, and the whole bubble is moving with the jet velocity. I think that's wrong. So, but the main problem is you would have got a higher rating for questions.
Okay, I didn't go any higher on the review, especially for one thing, as you asked for, as you stated that the opponent should have asked for a clear comparison between theory and experiment, which was obviously not presented in the report, so there was no theoretical model that could have been compared to any of the measurements conducted. And if you come up with a statement like that, I would have, or my question would be like, what the theoretical model would precisely look like. So I would have liked you to come up maybe with a complete model, or at least stating how you would actually deduce a model for the experiments that were presented in the report. So I mean, it's always easy to claim that there was no conclusion and there was no comparison. But if you come up with that statement, you need to have an own idea of that. So this is basically what I was missing in the review. Any more general comments? Any more justification needed? Because if not, we take a 5-minute break and then continue with the third stage. Thank you.